Okay, I guess it is recording. Good. And share. All right, 49. All right, I think I'm going to get started. Anybody in the waiting room? Looks like no. All right. Okay, so I'm going to keep going with Unit 3. And I'd like to stop about a half an hour before the end of class to take your questions, unless I have like a huge clamoring on the chat for how you need more time than that. Right. Nobody said anything, so I don't know. I assume everything is okay. So I'm going to go over, I am recording this. I'm going to go over a few things that I did in class last time. And the stuff that I'm talking about today is really pretty important for answering some of the questions that you'll have in the lab this week on structure and solubility. So anyway, in the last class, I talked about, I'll get that black pen. I like the black pen. I talked about two factors that determine whether a solvent will dissolve in a solute. Whether a solute will dissolve. And of course, it would be in a solvent. And the two factors that I'm talking about are what I call the entropy factor. And then there's the energy factor. Okay. And really, it's these two things that determine whether a solution will form. The entropy factor is what I refer to as the natural tendency for substances to mix. Okay, so things tend to mix in nature, things get more disordered, not more ordered, and that happens naturally. So this favors, this is like the disorder, disorder increases. Disorder is like mixing. Mixing things up is disordering it. Or entropy, which is like disorder, increases. We'll learn more about entropy later. And this always favors forming a solution. So entropy always has the same opinion about whether it wants two things to dissolve. Disorder favors dissolving. And then we have the energy factor. Okay, and this is actually governed by this thing, delta H solution.
Wait, Professor.
Which sorry.
You said entropy always favors
forming a solution.
Oh, forming. Okay, thank you.
Forming a solution, exactly. Yes, please interrupt me if you don't understand something like she did. Okay, so this energy factor is delta H solution. So that's why you could think about if you have energy here, and you have this line here represents the energy of the separated solvent and solute. You don't know how much I wish that solvent and solute didn't each start with the same 3 letters, because I can never abbreviate them. So anyway, but that's the way it is. So this would be the energy of the separated solvent and solute. And then, you know, you could have an energy of the solution. And as I said, it could be above or below. It could be an uphill process, a same energy process, or a downhill process. And this difference here, this energy difference, is called delta H solution. And last time I showed you that this is really the sum of 3 different contributions. So I talked about the dissolving process and this delta H solution being that difference in energy between separated and solution, that it can be positive, it can be negative, or it can be 0. And it depends on the intermolecular forces between the molecules when they're separated and when they're together. So between molecules of the solute, of the solvent, and of the solute and the solvent, which is what you get after a solution forms. Okay, so I showed you a diagram that sort of represented the 3 steps, the 3 different energy changes that are important in this process. And I called one of them delta H solute. So you have a solute, it's a bunch of molecules all together, and you need to separate them to put the solvent in between when you dissolve, okay? Because they attract by intermolecular forces, when you pull those molecules of the solute apart, it requires energy because you're going against the attractions, okay? So delta H solute is going to be positive, but the magnitude, which means whether it's strong or weak, the magnitude, the strength, or the magnitude is just the size of the energy change. It depends on the type of intermolecular forces in the solute. So in other words, between solute molecules. Okay, and then we have delta H solvent. Okay, and that is really the same thing, except it's pulling the solvent molecules apart so the solutes can get in between. And so that's also positive because it's going against those attractive intermolecular forces. And again, the magnitude, the size of this energy change depends on the intermolecular forces between the solvent and the solvent. And finally, when you put these together, you get delta H mixing, which is when the solute and solvent come together. And of course, all molecules are attracted to each other, even if it's only by dispersion forces. So those attractions mean more stable, mean a decrease in energy, and it depends on the solute solvent intermolecular forces between the solute and the solvent. And if you add all these 3 together, that's when you get the delta H solution. And that's the thing I illustrated over here. That can either be the sum total can either be that energy has to go up, that energy doesn't really change, or perhaps that energy is even released. So delta H solution can be positive, negative, or 0, depending on these different contributions. Now, I showed you a diagram last time, but here's a slightly different looking diagram. It's really the same thing. So if you have a solute and you have a solvent, this, by the way, this is in reading number 1. So on Blackboard, you know, I have written something for you to read about this process. Reading number 1, it's about molecular compounds, which is what we're talking about at the beginning of today, and what's dealt with in lab. That's all molecular compounds except for one NaCl. And then I have reading number 2, which is about what I'm going to start later today or and finish next time, which is about ionic compounds dissolving in water. And so that's another good thing for you to read. But in reading number 1 has this diagram. And so it basically says you could take the solute and the solvent, mix them together, and you know, you could think that it all happens all at once. Okay, so you get a certain delta H solution. But if you want to figure out, oh, you think my sound isn't doing very well? Is that still true? Morgan, is it still the case? What can I do?
Just every now and then. I don't know if it's my computer or if it's on your end.
Is it okay for others?
I can hear you fine.
Yeah, I hear you perfectly fine.
All right. Anyway, but if you break it up into steps, and this is what I talked about last time, you know, and just now, this is the delta H solute step where you can separate the solute. This is, so basically this thing happens overall. It just happens. But if you think about it in terms of the steps, then you can understand some of these energy changes, okay? Breaking apart the solute, not breaking any bonds, any covalent bonds. It's just intermolecular forces. And so it still requires energy, the amount of which depends on whether those forces are weak dispersion forces or strong hydrogen bonds, okay? And also you could think about breaking, you know, about separating solvent molecules and then putting them together. So this is like your third step where they end up all together. So this is just a diagram talking about how you can think about this. And I showed you another diagram last time. It's whatever you like. It's whatever diagram makes you understand this better, okay? So does anybody have a question about this? Because really now is the time to ask. Something is confusing to you. Okay, well, stop me if you have a question. So I want to go over the results that we did. This is from last class. We were talking about dissolving. So this is all about molecular compounds, this part. We're talking about dissolving the molecular compound pentane into the molecular compound water. I didn't put water structure here, but we all know what the structure of water is. Okay, it's got those lone pairs that I didn't show, but that's fine. Now this is pentane. You've got 5 carbons, hence the pent symbol, and all of those carbons are attached to hydrogens. So here's pentane and water, and we are considering the solubility. So is pentane soluble in water? That was the question we addressed last time, and I just want to go over the results. Pentane is a non-polar compound, CPD, that's my compound abbreviation. It has no dipoles because there is no electronegativity difference of bonds that is greater than, that is 0.5 or greater, okay? So what type of intermolecular forces can there be in a sample of pentane? So just please chat me an answer. Maybe you did already. No, because I hadn't asked yet. Oh, dispersion, right. I got somebody telling me the answer, and that's right. Only dispersion forces. That's the only intermolecular force. Now, rather than just knowing that, we try to say, well, okay, if those forces are dispersion forces and we're pulling pentanes apart from each other, that requires energy to overcome those dispersion forces. But because these dispersion forces are weak, it doesn't take too much energy to pull solute molecules apart from one another. To pull pentane solute molecules apart from each other. So that means that although you have to go a little bit uphill in energy, you have to supply some energy to do this, to pull them apart. So delta H solute will be positive, but it's going to be relatively small because the forces are relatively weak. Okay? Now, water is really very different. And as you all know, water has this hydrogen bonds. All right, so it's this dotted line here. That's the hydrogen bond between the delta positive of 1H. Remember, for a hydrogen bond, you have to have a hydrogen that's covalently bonded to an O that is or an ON or F, here it's O, attracted to an O on another molecule. This is a hydrogen bond. This is not a hydrogen bond. That's a covalent bond involving hydrogen and oxygen. Okay, so that's a covalent bond. So anyway, and you have a lot of these in water. You know, you don't just have one necessarily. You can have, you know, this whole network. You can have a whole network of hydrogen bonds, and you've got to break them. All right. So breaking hydrogen bonds, if you think of these intermolecular forces, you have hydrogen bonding, and you have lots of it. That's because every single atom on a water molecule is able to form a hydrogen bond with another water molecule, even though they won't necessarily all do that. They have what we call 3 sites, 3 places for hydrogen bonding on every water molecule. Every atom is a site for hydrogen bonding or potential hydrogen bonding. So that means it's going to require a lot of energy. I mean, not as much as breaking covalent bonds, but for breaking hydrogen bonds, you know, it's a lot of energy in terms of the, you know, the scale of intermolecular forces and what those energies are. It requires a lot of energy to separate water molecules. So delta H solvent is going to be positive, but it's going to be large. It's not going to be small because of all the hydrogen bonds that have to break. Okay, so now, we've taken care of the first 2 steps. Those are the uphills. That's the uphill part. But now we're going to go downhill. Now we're going to release some energy. So when pentane and water mix.
What does LG mean?
Large.
Oh, large. I'm sorry, I need it written.
Probably thought it was some chemical term, you know. Like,
Yeah, sorry.
that's okay. When pentane and water mix, some energy will be released. That's because all molecules attract. Because at least they could attract by dispersion forces. Now, when you have pentane with no dipole, right? No dipole, and water that is very polar. Water has a nice dipole, but if pentane doesn't have a dipole, you know, it can't interact with it by dipole-dipole forces. It can't form a hydrogen bond to it. So the only forces, the only intermolecular forces, I should say, between pentane and H2O are dispersion forces. And while these are attractive forces, and when you have attractive forces, what happens to the energy? Does it go up or does it go down? Does it get less stable or more stable? If you put 2 things together that are attracted, that's more stable. The energy goes down, okay? So they're attracted by dispersion forces. The only intermolecular forces are dispersion forces. So these forces attract H2O and pentane, but not a lot. but not much. And that's because dispersion forces are pretty weak. So if I want to figure out what is delta H mixing, first of all, what is the sign of delta H mixing? What does it have to be? Which way is the energy going for the mixing portion of this process?
Going down.
Going down, absolutely. That means that the delta H mixing is negative, okay? Is it going to be large or is it going to be small? You have to think about what type of forces. If you're forming hydrogen bonds, that releases a lot of energy. If you're forming dispersion interactions, those attractions are weak. You're only releasing a small amount of energy. So yes, whoever said Ashley, that's right. Negative and small. So when we go to add these things together, okay, we have delta H solution is delta H solute. See where I can't just abbreviate it as SOL. I got to write the whole darn thing out. I can't stand that. Okay, so this is the energy to pull solute molecules away from each other. That was positive and small because the solute was pentane. Pentane can only interact by weak dispersion forces. Then here you've got this delta H solvent being water, that's positive and very large because of hydrogen bonding. Dispersion forces I put there. And then delta H mixing is negative, but it's pretty small because H2O and pentane can only interact by dispersion forces, which are weak. And so when you look at this, you can see that it's really dominated by this term here. This dominates the picture. And so what you have to think about is, okay, you're breaking up hydrogen bonds, which requires a lot of energy, but you're not getting much energy back. You're not releasing much energy. It's requiring a lot of energy, but it's not releasing much energy. So the overall will be pretty large and positive. So that means delta H solution will be large and positive. And if we go back to that energy diagram, remember I said that there's three possibilities here for separated to solution. It could go up, it could be like this, or it could go down. And so in this case, this is the situation. It's going up. The delta H solution is a large positive number, so it's going uphill. Okay, so.
Professor, can I just stop you for 1 second before we keep going? You said, so for the delta H mixing is negative because what is going down?
Yeah, the delta H mixing is negative because after you've separated the solute and separated the solvent, let's say you actually do it that way. And then when you put them together, right, now they're interacting with each other, okay? And that interaction is an attraction. All molecules are attracted even only by dispersion forces. So the energy goes down for that attraction, but it doesn't go down that much because it's a weak attraction. You had to break up a very strong attraction, right? This hydrogen bonding, but you only get back, you only go down a little bit. See what I'm saying?
Yes. I'm gonna have to go over that again later.
I mean, you have to understand that molecules do attract one another. They could be attracted relatively strongly if there's a hydrogen bonding forces. They could be attracted relatively weakly if there's dispersion forces.
Right.
Breaking up dispersion forces doesn't take much energy.
Okay.
Breaking up hydrogen bonds takes a lot more energy.
Yep.
And then when you put them together, now you can't have hydrogen bonding anymore because pentane doesn't form hydrogen bonds with water, right?
Okay.
So you're only getting back a little bit of energy because you don't have anything for water to hydrogen bond with, right?
Okay. Yep, that makes sense. Okay. Thank
Okay.
you.
Hope so. Anyway, I'm going to be harping on this for a while. So if you don't get it the first time, you might get it the second time. But you should ask those questions. I'm happy to answer them. Okay, so we have a delta H solution when you try to dissolve pentane in water, a non-polar solute, right, into the very polar and hydrogen bonding H2O. You have a large uphill, a large positive delta H solution. That's what that energy difference is here between separated and solution. And so if it were only a little bit of an uphill, okay, then entropy really could overcome that because there is always that sort of driving force for things to mix together. There's always a tendency to mix, okay? So entropy does play a role. Entropy always favors a solution forming, but it cannot overcome a large positive delta H solution. If it was small positive, or maybe the separated and solution had about the same energy, or even if energy was released, then a solution would form. But if it's a large positive delta H solution, entropy cannot overcome that. Okay, so that's another step in the understanding of this process. Okay, so that's what you have to look for, really. If you see that if you use this reasoning and you find out that the solution and the separated solute and solvent and the solution have about the same energy, then entropy is going to win because energy isn't really playing a role. If it's releasing energy to form a solution, well, okay, then of course the system wants to get to the lowest energy, and entropy also favoring mixing means, yeah, they're both applauding. They're both like patting each other on the back, entropy and energy. They're saying, yeah, we really get along this time. We both want a solution to form, okay? But when you have that large positive, that's when you have to say, put the brakes. This is not going to form a solution. No matter how much entropy wants these two things to mix, there's just, the energy cost is just too high. They're just not attracting each other, and it's going to be two layers. They're going to like push away from each other. I don't know. Anyway, so I'm going to do another example. To give you another, more of a feel for this. So this is activity 2. There's actually a tiny little insect flying around that's driving me crazy. I have no idea what it is. All right, so this is really what we did for pentane, but it's for a different combination. We're talking about methanol as the solute and water as the solvent. And here's a picture of methanol. I often refer to it as MEOH, okay? It's just a CH3 and an OH. Okay, so what forces must be overcome? What happened there? I didn't touch a thing. It just did it spontaneously. So anyway.
I was gonna say, did you stop sharing?
I did. I could see that it did, but I didn't even touch it. So I don't know what happened. But anyway, so now what you have to think about is this 3-step process, right? We talk about pulling molecules of the solvent, separating molecules of the solvent apart from each other. So then you have to think about, okay, what intermolecular forces are there going to be between methanol molecules? And sometimes it helps to draw a diagram. So here is a methanol, here's CH3, OH, okay? That's methanol. And so if I draw another methanol, here's a CH3, OH, and now you could see that there can be hydrogen bonding here because look here, you have an H that's covalently bonded to an O, right? That is attracted to an O on another molecule, okay? So we have this interaction, which we call a hydrogen bond. Okay, so what forces must be overcome between methanol molecules? The answer is hydrogen bonding. And that's because methanols are able to hydrogen bond to one another. So what is the sign of delta H solute? You know, you should actually be able to answer that question before I even tell you what molecules are involved. Because delta H solute is the energy change when you pull molecules apart from each other. Molecules of the solute. No matter what they are, it's going to cost energy to do that because the molecules are naturally attracted to each other. So you should know that this is positive. Delta H solute is always positive. Delta H solvent is always positive. It's the large, small, or medium that is the kind of judgment call. And that's dependent on the type of intermolecular forces that are between these molecules, okay? So what is the sign is positive? What is the magnitude? Well, you're breaking hydrogen bonds. So what am I going to choose here? Is this large or small if you're breaking hydrogen bonds?
Large.
It's going to be large. Yes. LG for large, okay? And that's because hydrogen bonds have to break between methanol molecules. And these are pretty strong. These are the strongest intermolecular forces. Okay, so that's why delta H solute is large and positive. Okay, so now we're going to move and look at water. Water is our solute. Sorry, our solvent. And we have water. And, you know, we have tons of hydrogen bonding in water. I wouldn't say that it's a continuous chain of hydrogen bonds, but, you know, in a liquid, there's probably, you know, some that the chain would break, whatever. But there's quite a lot of these guys here, okay? And you have to break these to separate. These aren't covalent bonds, but you must. Somebody in that waiting room. Yeah, oh my God. You must break hydrogen bonds to separate these solvent molecules. That requires energy. That means that the sign of the delta H solvent is going to be positive or negative. It requires energy. Positive, exactly. Requires energy to break hydrogen bonds. And it's a fairly large amount of energy as intramolecular forces go because it's hydrogen bonding. So delta H solvent is large and positive. But now we have a really very different situation from when we had pentane in water. We have methanol in water. And what can methanol in water do that pentane in water couldn't do?
Form hydrogen bonds.
That's right. It can form hydrogen bonds. And that's exactly what happens. You get hydrogen bonds form between methanol and water. And these are strong intermolecular forces. They're just as strong as the ones between methanol and water, okay? And there's really more of them because you have all those methanols and all those waters that get to come together, okay? So what is the sign going to be here? Is the sign going to be positive or negative? If you're bringing them together, there's an attraction. So what is the sign? Anybody? Negative, negative. Releases energy due to the attractions. And the way you can think about that again is that when something is attracted, it's more stable when it's with that other thing than when it wasn't. So it's lower in energy, more stable. Okay, and delta H mixing is going to be large and negative because of hydrogen bonding. Between methanol and water, okay? That's what it's intermolecular force between those two things, okay? So what about our delta H solution? What do you think the sign of the delta H solution will be? Let's sum it all up. You know, we have delta H solute, delta H solvent, and delta H mixing, okay? Delta H solute, that was a solute was methanol, forms hydrogen bonds. So we had a large positive. The solvent was water, has hydrogen bonds, takes a lot of energy to pull those hydrogen bonds apart. But when they come together, you get all that energy back, all the energy that it took to break up those hydrogen bonds. Now you're forming them between methanol and water. So it's really a wash, honestly, energy-wise. This ends up being about zero because the hydrogen bonds that were broken are made up for by the hydrogen bonds that form. Okay, so I would say that the delta H solution is near zero. Okay, so if I wanted to draw a diagram of my separated solute and solvent separated with energy over here, okay, and now the solution, it's like delta H solution is near zero. There's basically no change, okay? Somebody thought it would be large positive. Why did you say that, Chanel?
I realized I was wrong. I think just because of the previous problem, I was thinking that it was that, but I realized that the sizes were different, but the charges were
Some
the same.
people think because you have two large positives here and only one large negative. But if you think about it, you know, here you have half the molecules that are methanol, half the molecules that are water, and here you have them all together. You actually would have about the same number of interactions. So yeah, anyway, I thought that's what maybe you were thinking. All right, so overall, it says here, I think overall delta H solution would be near zero. Okay. I think that the magnitude would be near zero, because if it's near zero, we don't say it has any magnitude. If it's large, we do, or small. And so we basically have an energy diagram where there is no big change. No, let's just say no change in energy. So what this kind of means is that the energy aspect doesn't really matter. That energy doesn't care, you could say, or energy doesn't really play a role. So if the delta H solution is near zero, then energy doesn't really play a role. It's like it's a wash. It's the same amount of energy as needed as what you get back. So there's basically a net zero change in energy. So in that case, what happens? Okay, so if energy doesn't care, then entropy is going to take over. And what about entropy? What does entropy always lead to? What does entropy always favor? Always favors what?
Solution.
Solution, exactly. Okay. And so a solution will form. So they would dissolve in each other. And indeed, methanol is infinitely soluble in water and vice versa. So in this case, the energy of the solution, right? So the energy of the solution is like the energy over here, what you get, the energy of the thing you get. It's basically about the same as the energy of the separated solvent and solute, which doesn't influence forming a solution. So in that case, the natural tendency to mix, which favors, always favors forming a solution. Natural tendency to mix favors forming a solution. So which wins? You know, we have energy, we have entropy. Well, energy, remember I said that this is really doesn't play a role because there is no change in energy. So I say entropy wins because energy doesn't care. Okay. How does that sit with you folks? Pretty good? Anybody got a question? You know, even a question you think might be a dumb question.
Professor?
Yes.
Yeah, so you said energy doesn't care. Is that in all cases or just like cases like this one?
It's energy doesn't care in cases when delta H solution is near.
Is zero.
If,
Okay.
if this delta H solution is large and positive, yeah, you can bet that energy is going to play a role. It's not going to dissolve. If delta H solution is negative and energy is actually released when you form a solution, then entropy and energy both favor forming a solution. So there's nothing to go against forming a solution. But in a case when delta H solution is about zero, that's when we say energy doesn't care. Then,
Okay.
only then. Good question. Yeah.
Thank you.
Yeah. Any other questions? I have a lot of people here. Must be another question. No? Okay. All right. Well, moving along then. I have this table. This is activity 3, and I'm not going to fill it in this tiny little space. I've sort of expanded it. I'm going to talk about it as we go through. So what is this table? So I'm trying to address the oversimplification of a statement like dissolves like, okay? People say that things dissolve in each other when they're like the thing that they're dissolving in, okay? Things that are alike will form solutions. Things that are not alike will not form solutions. And, you know, that's a wonderful high school statement, you know. It's just something that you can remember very easily, like dissolves like. But to really understand why, that's what all these energy considerations and entropy considerations will give you. And so I want to come up with some kind of understanding of the expression like dissolves like that is beyond, oh, well, people tend to stick together that are like each other. I mean, molecules are not people, so that really doesn't make any sense. So I wanted, you know, why does it make sense? So I'm going to try to show you 4 different situations here, which a couple of, let's see, I think that, yeah, a couple of them we've sort of addressed already, but anyway, And what I want to do is make a general statement when I'm done. Okay, so let's take a look at this. So if you have a solute that can form hydrogen bonds, all right. Now we did a solvent that can form hydrogen bonds and a solute that was, and actually we did this example, right? Solute able to form hydrogen bonds and solvent able to form hydrogen bonds. That was the case with the methanol and water that we just talked about. Okay. It was, as we talked about, the delta H solute, remember, this is for pulling apart those methanol or whatever solute that forms hydrogen bonds. It's always going to have a large positive delta H solute because you're breaking hydrogen bonds. Okay, and that costs a lot of energy. Delta H solvent is also able to form hydrogen bonds. Sorry, the solvent is also able to form hydrogen bonds. So that means that delta H solvent will be large and positive for the same reason. Okay, we just did this example. Delta H mixing, though, is going to be large and negative. Okay, and that's because you're forming hydrogen bonds between the solvent and the solute. Okay, and the sum will be near zero. Okay, in this situation, like I said, energy doesn't care or doesn't play a role. Okay, entropy, however, always favors forming a solution. Will a solution form? The answer is yes. And that's because entropy wins when energy doesn't play a role. So that is really just a review of what I just did, really. For methanol and water, that's an example of that. But there are tons of other examples of that as well. Okay, so let's think about a nonpolar solute and a nonpolar solvent. All right, so say we had something like butane in pentane.
Excuse me, Professor. Would you be able to just scroll up a little bit, really fast?
Okay. So if you have, and these are all hydrogens here, just too lazy to draw them. But, you know, if you have this situation, butane in pentane. Oh, it didn't come. Let me just fix it a little. There we go. Butane is 4 carbons. Pentane is 5 carbons. Okay. What would be the sign of delta? What I can put the signs in right away. Delta H solute will always be what sign? Is it going to require energy to pull apart molecules or release it? Molecules are attracted, right?
It's positive, right?
That's right. This is always going to be positive. This is always going to be positive. This is always going to be negative because this is pulling apart molecules. This is pulling apart molecules. This is putting molecules together. You see? And I'm not talking about pulling apart covalent bonds. I'm talking about pulling apart intermolecular forces. I'm not pulling the atoms of a molecule apart. I'm pulling molecules apart from each other. So we know that's always going to be plus, plus, minus here. So the question is, what about the magnitude? Now, for either butane or pentane, whichever I assign to be the solute, what are the types of intermolecular forces that are between butane molecules or between pentane molecules? What type of intermolecular forces are there? What about for butane? Dispersion. Somebody said it. Are they strong or are they weak?
Weak.
They're weak. So is this going to be large or small here? If they're weak. The weaker the forces, the easier it is to break them, right? So this is going to be small, okay? Right, a few people said it, good. Similarly, because these two molecules have about the same type of forces, it's going to be small positive for the pentane. If the pentane is the solvent, doesn't really matter here. Okay. And when you put them together, what type of forces are they going to interact with each other by? Yes, dispersion forces. So here you're breaking up dispersion forces. Here you're forming, they will interact by dispersion forces. So basically it requires a small amount of energy to pull solute molecules apart, same for solute. And then when you put solvent and solute together, you get the same type of interaction, you get the same amount of energy released. So what is the delta H solution going to be in a situation like that? Near zero. Yes. I think you're catching on. So will a solution form? Well, energy doesn't care or doesn't play a role. So entropy is going to win, and entropy favors a solution forming. Why? Because things tend to disorder, and that will mix things. That will not unmix things, right? If you mix, water and vinegar, shake it up, and you leave it there, it's not going to become vinegar and water again. Anyway, it's kind of a stupid example, but whatever. Especially since vinegar is already a solution of acetic acid and water. But anyway, entropy will win, and then a solution will form because this is near zero. And the only other thing is something that definitely favors mixing. So, I just try to make things too pretty. I'm kind of a perfectionist. All right, so that's that. Now let's consider a solute that can form hydrogen bonds, but a nonpolar solvent. Okay, so now what can I put in here right away? Delta H solute, solvent, and mixing. What can I fill in right away under solute? What sign? Does it require energy or release energy to pull molecules? Positive. What about this one? Same for the solvent, right?
Yeah, it requires energy.
And then for the mixing is releasing energy. Okay, but now it's the large and small that we have to think about. So if the solute can form hydrogen bonds are strong. So it requires a lot of energy to break up those hydrogen bonds. So that means that this is large and positive. The solvent, however, is nonpolar. So if it's nonpolar, what type of forces? So the solvent molecules interact by what type of dispersion forces, right? Are these strong or are they weak? Come on, good, chat. They're weak. So what is this going to be here? If they're weak, you're breaking up weak forces. That requires a small positive in energy, a small uphill energy. But when you put these guys together now we're talking about a solute that can form hydrogen bonds. So that's kind of like, you know, maybe water or methanol, and a solvent. So these are just examples. And a solvent that can't. All right, it's non-polar. I'm taking up the room for the next thing. So maybe this would be pentane, right? So this is, yes, this is going to be small negative, because the only interactions you can get between a nonpolar solvent and a hydrogen bonding solute, doesn't matter that that solute can form hydrogen bonds with other solutes. It can't form them to a nonpolar solvent. So you cannot form strong hydrogen bonds between a nonpolar solvent and a hydrogen bonding solute. Do everyone understand what I mean there? Because I call something hydrogen bonding when it is able to form hydrogen bonds. And the the solute is hydrogen bonding, we call it. The solvent is not, it's nonpolar. So you cannot form hydrogen bonds. What can you form? Only dispersion forces are possible. And these are weak. So while energy is released, not much energy is released. Okay. So it looks like, again, this is dominating the picture. No matter what you do, if you're breaking up hydrogen bonding in a hydrogen bonding solute, you can't get that energy back unless you put it with another thing that can also hydrogen bond. Okay, so in the end, we're going to have a large positive here for a delta H solution. And so what happens when that's large and positive? So now we have the situation like this, you know, we have a big, large, positive delta H solution. But here's the solution, here's the separated, here's the energy, right? So it's a large positive delta H solution. Well, entropy always wants mixing, but it cannot overcome a large positive delta H solution. So will a solution form here? It will not. That's right. Somebody wrote, energy wins and no solution can form. Energy wins. Entropy cannot overcome a large positive energy cost. Okay. So I'm going to move on to the last example. And that is, let's say you have a polar solute. So let's say you have, notice it doesn't say hydrogen bonding, it just says polar. So here's an example. This is acetonitrile. And it's quite polar. It has a nice dipole here between the C and the N. Okay, this is delta negative and delta positive. This is a pretty good size, well, reasonable dipole. And let's say that that's your solute. And let's say that you have, say, acetone. Here's acetone. I'm going to show you H3C, C double bond O, CH3. Okay, so this is just, I just don't want to draw it out, but it's really, you know, CH3. So that's what I mean. I'm just going to write it as CH3. And here I like to write, you know, the C is what's bonded to this C, so I'll put H3C. So acetone here has a dipole. Now, why can't so this I'm going to call the solvent. This is acetone. If you get to take organic lab in person, which I certainly hope you do, you will see a lot of acetone. That's often used to rinse glassware because it dries quickly and things like that. So why can acetonitrile, why isn't it hydrogen bonding? Why can't you get a hydrogen bond between this nitrogen and a hydrogen on another molecule? So why isn't this hydrogen bonding a hydrogen bonding liquid? Why isn't it? Somebody answer me that.
No.
The H isn't directly bonded to the N. Yes, exactly. This N here, this H here, all the H's are bonded to carbon. And these bonds are not polar. And some of you in the something I corrected recently, graded assignment 2, formed hydrogen bonds all over the place from hydrogens that were bonded to carbon, and they are wrong. That is not right. And acetone, you also can't have hydrogen bonding because all of these H's here, all the H3C and the CH3 are all bonded to carbon. So they're not polar. So you don't have a situation where you have an H that's covalently bonded to O, N, or F. So these have dipoles. These have dipole-dipole forces. And these have dipole-dipole forces. Okay. Now, dipole-dipole, I would say, is kind of a medium force. So what about, so here, when I go to fill in, I know that this is going to be positive, positive, and negative, because it always is. But breaking up dipole-dipole forces, I would consider that to be medium. Okay. So breaking up, pulling molecules of acetonitrile apart from each other requires a medium amount of energy because you're pulling apart dipole-dipole forces. These are sort of medium in energy. So it requires a medium amount of energy to do that. Similarly, pulling these apart, this might be actually a little harder because this is a stronger dipole here. But I would still say medium. It's not a hydrogen bond. It was more than dispersion forces, okay? Now, when you put these two guys together, they will interact by dipole-dipole forces, okay? So CH3CN and CH3C, oh God, let's just call it acetone, will also interact, right? This is the solute solvent interactions by dipole-dipole forces. So that's going to release a medium amount of energy. Okay. So what about this delta H solution here? What about delta H solution then? Well, here's your energy cost. This is what the energy costs. And this is the energy released. And they're about the same. So what is delta H here going to be? Near zero, exactly. So will a solution form? Yes. Why? Entropy wins. Entropy wins. In other words, disorder wins, mixing wins. Energy doesn't care. Doesn't play a role. Okay. So when I ask the question, you know, this is like the $64,000 question, which, by the way, that TV program was before my time too. So I know it's before all your time, but we still use that expression. What's the big question, you know? Why does like dissolve like? Okay. So things generally dissolve in each other when the energy required to break intermolecular forces is about the same as the energy that's released in forming these intermolecular forces. So, so things generally dissolve when the energy required to break up solute, and solvent intermolecular forces is approximately equal, I guess I should write that out, about equal to the energy released when solute solvent forces form, intermolecular forces form. Okay. Well, when does this happen? This usually happens when the solvent and the solute have the same type of intermolecular forces. So this will happen when they're both nonpolar because they both have dispersion forces. When they're both polar, they both have dipole-dipole forces, or when they're both hydrogen bonding, right? So this generally happens when both, and by this I mean the solvent and the solute, have the same type of intermolecular forces. Okay. And that's when they, like, for example, both nonpolar. So the intermolecular forces for both are dispersion. Or if they're both polar, intermolecular forces are dipole-dipole. Or if they're both hydrogen bonding, intermolecular forces are hydrogen bonds. So when don't things dissolve in each other? And by the way, this is a gross oversimplification. And lots of polar things that are not able to hydrogen bond themselves will form hydrogen bonds with a hydrogen bonding solvent. So I'll show you an example of that. So it's oversimplification, but I think it's an important oversimplification. So when will things not dissolve? That's an important sort of other way of thinking about it. And that generally, when did we see that things did not dissolve? We had pentane and water. What was the thing about that combination that really led to them not dissolving? What was the energy cost that couldn't be overcome? Was it breaking up the dispersion forces in pentane? Was it breaking up the hydrogen bonds in water? Which of those was really important?
Was it the energy cost?
Yeah, but which was it? Was it breaking up the hydrogen bonds in water or breaking up the dispersion forces in pentane? Which of those costs more energy?
H bonds.
So when will things not dissolve generally is when hydrogen bonds, well, let me not be about that, when delta H solvent or solute is too large and positive, and the delta H mixing is not able to offset that with a large negative. So it's when delta H solvent or delta H solvent is too large and positive, and delta H mixing is not large and negative to make up for it. And I think it's best to think about this with an example. If you have a hydrogen bonding solvent, okay, like for example, water, and you have a nonpolar solute like pentane, okay, then these will not dissolve because this water has a huge delta H solvent due to breaking up hydrogen bonds. So that's one example. It would also be, for example, if you had a nonpolar solvent and a polar solute. Again, here you have dipole-dipole forces. And here you only have dispersion. So you can only have dispersion between the two of them. So, so you're not going to get that energy back. Okay. So I just have a little time before I want to stop and take your questions about the tests if you have them. But I want to say that chemistry is really not always so neat. You know, frankly, chemistry not being always so neat is really what makes it fascinating. You know, there's so much variation in chemicals and things that they do. But I want to give you an example. Here's a acetonitrile that I already told you about, this compound. What if you took and tried to dissolve this in H2O? Okay, I don't think I need to draw the structure of water. So acetonitrile here has a dipole, so it has dipole-dipole forces. And it has, of course, dispersion forces, everything does. Water has hydrogen bonding, and it also has dispersion forces. Okay, so I would say that delta H, if this is a solute and this is a solvent, delta H solute will be sort of medium and positive because you're breaking up dipole-dipole forces. Here, the delta H solvent will be large and positive because you're breaking up hydrogen bonding, okay? And when you put them together, you could see something interesting. Here's your acetonitrile, and here's your H2O. Can you form hydrogen bonds there? Here's a nitrogen. Here's a hydrogen that's covalently bonded to an O. Yes, you can form a hydrogen bond here. Okay, so delta H mixing is large and negative. So here we have a case where you're actually able to form hydrogen bonds between two molecules where one of them couldn't form them when they were alone, right? You only had dipole-dipole here. You had hydrogen bonding here, but now you have hydrogen bonds in between these two, the solvent and the solute. So what is the delta H solution going to be here? We have medium positive, large positive, and large negative. I would say that it's going to be either near zero or it might even be negative. Because you're getting more interactions between acetonitrile and water than you had between acetonitrile and acetonitrile, more stronger interactions. So there's some pretty interesting things that can happen here. So definitely it forms a solution. Okay, because if it's negative, it really would certainly form a solution. But, you know, things are not always that simple. And I'm going to talk just for a couple of minutes about alcohols. Now, we talked about methanol. That's CH3OH. On the other end, we have butanol. Now, butanol is the compound that I mixed with water in lab the other day. I mean, in lecture. Remember, I showed you a demo. This is butanol. And we mixed it with water. And if you remember, it formed 2 layers. Okay, it did not form a solution. Whereas methanol forms a solution with water. So, you know, this guy here has an OH. Butanol molecules can form hydrogen bonds with each other, but not so much, right? Because you've got 4 carbons here in the chain. Okay, so you will find, and because you're going to do, well, we're going to watch the video, but butanol does not dissolve in water. Methanol does dissolve in water. So one OH group, right? Butanol being able to interact with water through a little bit of hydrogen bonding is not enough to make up for this big part of the molecule here that's nonpolar. Of course, my pen stops working. So, oh, it's back again. Okay, so one OH on butanol is not enough to be able to dissolve in water. Okay. So this is something you should take note of, because in lab, we have lots of things like this, where you have one OH, but you have a lot of carbons. You have a giant carbon chain with an OH on the end. That molecule is going to behave mostly like it's nonpolar. And we're actually going to do CH3OH, CH3CH2OH, and also this one, which is 3 carbons and an OH. You don't have to write these down. This is for lab. And we'll see what the solubility of all these are in water. Okay, so I just want you to start with an open mind and not think that everything with an OH, oh, of course it's going to dissolve in water. Maybe not when you have a greasy 4-carbon chain hanging on to it, because you can see here that it did not dissolve in water. All right, so anybody have a question from the exam?
I just have one quick question.
Good.
I mean, it's not really pertaining to the question. It's more or less one of my files was corrupted, and I lost one of my answers. Would I be able to like maybe email you that or something? Because I had already submitted.
Yeah, please do.
All right, thanks.
Yeah, no problem. Nobody has a question?
Well, I have a question about, I have version B.
Version 2?
Yeah. I forget how to read the graph with the A, B, C, D on it.
Oh, okay. You're talking about, let me see if I can find that in the notes, because we did a lot on that. Oh, here it is. You mean this graph, this type of graph?
Yeah.
Okay, so what's your question about it?
I forget like how to read it.
How to read it?
Yeah.
Well, okay, so you have vapor pressure is plotted on the y-axis. What that is the pressure above a liquid sample, and temperature here on the other axis. So Are you concerned about like the boiling point being asked? Is
Yeah.
that
The boiling point.
okay? So what is the boiling point? Let me write the definition. The boiling point of a liquid. That is the temperature when the vapor pressure above the liquid equals what? What should I put in here? Somebody else answer that. The vapor pressure above the liquid equals what?
1 atmosphere or
Yeah.
760 torr.
Pressure, exactly. So, you know, those of us here living in Rhode Island, atmospheric pressure, that's pretty messy, which is 1 atmosphere or 760 millimeters of mercury or torr, okay? So when you heat up a liquid, right, you start out with, say, water, and it's like 25 degrees is room temperature. But if you heat it, right, what's happening is there's more and more gas molecules above that liquid until the vapor pressure above the liquid, that's the pressure of water, right? The water vapor is equal to 760 millimeters. When that happens, then when these bubbles start to form in the liquid, okay, they form at such a high pressure, it's equal to atmospheric pressure. Below that temperature, those bubbles form, and the pressure in the bubble is smaller than, and it collapses in the liquid because it doesn't have the pressure to sustain go through that liquid. So you get these big bubbles forming when the bubbles start to form with a big pressure, it's atmospheric pressure. So that's when you get that rolling bubbling action. But what the basic idea is, you know, vapor pressure of everything is going up with temperature. These curves are always going to go up. We know why. It supplies energy for molecules to get into the vapor phase. But when the pressure, so here you could see for water here, it's 200 millimeters or torr. Over here, now it's 400, right? Now it's 600. Well, over here, it's 760. You see that, Morgan?
Yeah.
So when the vapor pressure equals that 760, that's the boiling point.
Okay.
Okay. Now, if you had a high altitude, that would change the atmospheric pressure, be below 760. So that would boil at a lower temperature, depending on whatever the pressure was. Okay. Does that answer your question?
Yes, thank you.
Good. Anybody else? No other questions?
Professor, I have a question.
Good.
So I have version B as well, and I'm actually kind of confused on question 2. I can read it for you if you'd like.
Yeah, that'd be great. Hold on. Let me
Okay.
take notes while you're reading it. Question 2. Okay, what does it say?
It's a bad day in the lab. 2 students are doing experiments. Each is 15 feet away from the professor at
Okay,
the same time. Sorry.
students. Here's the 2 students. And they're each the same distance away from the professor. As a lady professor. Okay. And one has, oh, sorry, someone's trying to come in somewhere. Okay. Okay. And so one of them, what are the 2 chemicals?
One is NH3 and the other is H2S.
Okay, so one is releasing H2S gas into the air. The other is releasing ammonia gas into the air. And so what else does it say?
The professor has no idea that this has happened until she smells the first gas. Which chemical will the professor smell first?
Okay, without naming the answer here, what's going on here is we have these gases are diffusing. Okay. And we did a whole lab on gases effusing, right? And we said that the effusion rate is proportional to 1 over the square root of the molar mass. And then in lab, we said, well, okay, if rate is proportional to 1 over that, then the time will be proportional to the square root of the molar mass. Okay. Okay. Are you with me?
Okay, sorry, I was still muted. I didn't
Yeah.
realize.
So diffusion and effusion, they both depend on the root mean square speed. The speed, which is some kind of average speed, I'm going to call it, is basically the square root of 3 RT over M. That's how we get this molar mass. The proportion speed is proportional to molar mass, and diffusion rate or effusion rate is proportional to that same speed, which is why it's 1 over. So the bottom line is that the time of effusion is proportional to the square root of a molar mass. And the same is true of the time of diffusion. It's also proportional to the square root of a molar mass. Okay?
Okay.
So it's really the molar mass differences here that you have to think about. The fact that they are both 15 feet away is simply telling you that the student is the same distance away from the professor. Okay?
Okay. Okay,
So
thank
you're
you.
given a time for one of the gases, you should be able to find the time for the other gas based on that proportionality.
All
Okay.
right, thank you.
I have a question.
Okay, let's hear it.
All right, so for question number 12, could you explain it to me slowly? Because I've read this question like 5 times and it's just not going into my thick
So
brain.
what does it say?
Okay, so 54 grams sample of ice at -25 Celsius degrees is heated until it is liquid at 0.0 Celsius degrees. How much heat does the water absorb in this process? It says,
Okay, right. So it's heated until it's liquid at 0 degrees C, okay?
right, yes.
So what you need to do is think about the steps
Mm-hmm.
of this process, okay? So if you remember, I had a heating curve for water.
Okay.
And so what the heating curve did, it was the temperature, and this is added heat. And actually, the first thing on that graph was -25 degrees C. If you look at that diagram. And so it'll heat up, but when it gets to 0 degrees, what happens? So the temperature goes up
Mm-hmm.
until you get to 0 degrees. Now, somebody else can answer this. What happens when you get to 0 degrees? You're heating up ice.
It flattens out.
Melts.
Say that again.
It melts.
Yeah, it melts. Now, when it melts, what happens to the temperature? Does it continue to go up as it melts?
No.
No, it's constant until it finishes melting. When it finishes melting, so here you have solid. Here you have solid, but now you're going solid to liquid. Here you have liquid, right?
Mm-hmm.
And after 0 degrees, once you get to liquid at 0 degrees, and it's all liquid, then when you add more heat, what happens to that liquid? What does it do? What does it become? How does it?
Gas?
Sorry?
Does it turn into gas?
Well, not yet, right? Because it doesn't turn to gas until you get to 100 degrees, right?
Oh, okay.
You heat up the liquid now. At this point, your liquid at 100, so here your temperature is going up.
Mm-hmm.
The liquid temperature is going up, okay? Now you're at 100 degrees. As you increase the heat added, you keep adding more heat, what happens now? Does the temperature continue to go up? at 100 degrees. That's when you start to form gas. You know, when you're boiling water, you heat up that water. And once it starts to boil, it's at a constant temperature, right? It doesn't continue to get hotter. The temperature of that water will be 100, will stay 100 degrees C until all that liquid has been converted to gas, which doesn't happen. You know, you don't usually boil water until the pot is dry, right? You usually just, you know, but the nice thing about boiling water, it's so convenient because of this way this process goes. You don't have to worry about the temperature getting too hot if you're boiling something. You know, it's not going to go up infinitely. It's just going to stay at 100 degrees until it all goes to gas. Once it's all converted, and this is what happens in the microwave when the water in the popcorn bag is all steam, now that the temperature goes up like crazy. The temperature on the y-axis. So in your process, you have to figure out, you know, what steps do you have here? It looks to me like you have ice that's being heated. And the temperature is going up. So the temperature is going from 25 degrees to 0 degrees, right? And then you're doing, and then you end up at liquid. So this is your stopping point, right? This is where you start. And this is where you stop. Okay. All right. So if you remember when I talked about this, I talked about the sloped parts of the graph, these 3 parts of the graph here, that they use the equation. Like this is when these are the sloped sections, use that the heat is mcs delta T. They all have a change in temperature. They all have an initial temperature and a final temperature. But for these horizontal pieces, like this piece here and this piece here, okay, the horizontal pieces, these are the phase changes. And these are at a constant temperature. And these use the equation Q is the number of moles times the delta H. It would be the delta H fusion for this one, but it would be the delta H vaporization for this one. So I'm going to put fuse or vape. And the reason why we need the number of moles here is because this is a per mole quantity.
I think I know what I'm gonna do. Thank you so much. That actually clarifies it.
Okay, good, because I think this is good for everybody, because I didn't give everybody the same 2 processes. But you know, some people will have different processes, but I think this conversation here works for everyone, because while they're all different, they all follow these same, you have to figure out what your steps are. You're going to have one heating step and one phase change step. That's true for everyone. Might not be the same order, might not be the same temperatures, but okay, good.
Thank you. I appreciate it.
You're welcome.
I have a question.
Okay, Stephanie.
Yeah, I have version C or 3. So it's
Why don't you just tell me what
yeah, it's question 8. Question 8.
What?
Question 8, letter C. It's what's the normal boiling point for substance C? It's the graph.
I think that's kind of like what I was talking about before, right? Do you want, is it normal boiling point that's confusing you?
Yeah, I think so.
The normal boiling point is the boiling point at sea level. And at sea level, the atmospheric pressure is 1 atmosphere or 760. You see what I'm saying here? Is that what you needed to know? Because I've already told you about the boiling point, right? I went back to that section. I don't remember where it was. Where was it? Here. Remember I said the boiling point is when the vapor pressure goes up high enough that it equals atmospheric pressure. So this line here is giving you the normal boiling point of all of these liquids, where they equal 760, which is 1 atmosphere. Are you understanding what I'm saying?
Yeah, I got it. Okay, I got it now. I got
All
it.
right,
Yeah,
good.
thank you.
You're welcome.
This is due at 11:59 p.m., right? Today?
You know, actually, my deadline that I put that as a deadline, but if you hand it in before tomorrow at 2, it might say late, but it would accept it, and it doesn't matter.
Okay.
Professor?
Mhm.
Yeah, so I have a question. For the last question, 14D, it asks to attach a page and explain the and compare the intermolecular forces of the compounds. And it says to calculate the molar mass of each. I don't get like how we're gonna use that to compare the
Because one kind of force is dispersion forces, right?
yeah.
And dispersion forces, the magnitude, the strength, right? The strength depends
On the molar.
on the size of the electron cloud. I talked about that a little bit. And the size of the electron cloud is larger when the molar mass is larger. And the reason for that is the bigger the electron cloud, the further away the electrons are from the nuclei. And so they're not held as strongly. And they are what we say is more polarizable. Because this whole dispersion force thing depends on how, you know, the electron cloud can float around and become polarized with more on one side than the other, right? More electrons on one side, the nuclei more on the other side. So to be complete about comparing the intermolecular forces, you have to compute the molar masses, because you can have one molecule that has a much higher molar mass than another, or you can have molecules that have very similar molar masses. But, you know, dispersion forces are important. They're not the most important force. I would say that's how they're important, but they're not like hydrogen bonding. But still, in order to be able to make a valid comparison and give evidence, in other words, saying, oh, this guy has lower dispersion forces than that one, then you need to be able to, you need to know what their molar masses are to be able to say that.
Yeah, thank you.
Haley, did you want to ask me anything about that? Why did you write that about getting out of work at 2:30? Was that for me or for someone else?
Oh no, that was just because when you were saying that like submitting it late by 2 tomorrow, but like I'm at work all day until like 2:30.
All right, I tell you what, I'm going to make it tomorrow at 11:59.
Okay, thank you.
All right. Anybody else have a question?
Just to clarify, did you just say that the exam, we can hand it in tomorrow by 11:59?
Yeah.
Yeah. Oh, okay. Thank you.
I'm going to change that right after class.
Okay. Thank you, Professor.
You're welcome.
Professor,
Yeah.
another question. So is it a must to type in Word or can we handwrite it?
Is it a really big burden for you to do that typing? Is that a
No,
problem?
I'm just asking. Like, it's not a problem, but it's easier for me to handwrite it.
That last one, I really would appreciate it typed. You don't have to do the whole exam type, but just that last one might be a paragraph.
Oh, okay.
And
I'll
type
just
space, don't put it single space.
okay. All right. Thank you. Have a good one.
Bye.
Bye.
Thank you. Have a nice day.
Bye. Bye, everybody. See some of you in lab tomorrow. All right.
I have a question.
Oh, good. I almost closed the meeting. Good thing you spoke up.
Sorry, I have a question. So I have version 3 question. Question 1 is just throwing me off, and I think
This
I'm kind of
question one say, can you just read it to me?
okay. It says this reaction occurs in a large test tube at 35 Celsius, and it has a whole equation. So it's 2 aluminum solid plus 6 HL aqueous yields 3 H2 gas plus 2 AlCl3 aqueous. A tube going through the stopper of a test tube feeds into a graduated cylinder that has been inverted in a tub of water. At the end of the reaction, the total pressure of gas is an inverted cylinder is 527 torr, and the volume of gas collected is 405 milliliters. What is the mass of the aluminum must have reacted?
All right, so this is a picture of what's going on here, okay?
Okay.
This is what you, by the way, if I was doing this problem, I was a student, first thing I would do is draw a picture like this, okay? Because so you've got this reaction. Can you see the arrow here?
Yes.
Got the reaction going on here. It's generating a gas. That gas is going through this tube and is ending up in here, okay? This is where the H2 gas is ending up. You understand that?
Yeah.
And you're told what the pressure is at the end of the reaction, and you even know what the volume is. That's referring to this space right here. Okay?
Okay.
So you need to calculate something you need to calculate the moles of something in this equation that's going to allow you to calculate the moles and then the grams of the aluminum that reacted. Right?
Yeah. Okay.
Okay, so the fact that you're collecting this over water here, what else is in this? What else is in here?
Gas.
What gas? Besides H2, what else is in there?
O2 AlCl3 aqueous.
Wait a minute, AlCl3 is aqueous, it's over here.
Where?
HCl is aqueous, it's over here. It's only the H2 that goes up this tube. But there's something else in that space with the H2. And it has to do with how this gas was collected. How was this gas collected? What does that mean when it's collected over water? If you have a glass of water, what's above the glass of water always?
Air.
I could be I could be on the moon and there's no air, right? I mean, it's only air because air happens to be there. But what is always there, because this is liquid water?
Is it water vapor?
That's right. This is water vapor. So at the end of this reaction, you have the vapor pressure of water here because you always have water vapor above water. So this pressure here includes those two pressures. Okay. So what you have to do is you have to find what the pressure of the H2 is, because you know that once you have this, you can get the moles of H2 through the ideal gas law. Okay, given the volume and you're given the temperature, right?
Right.
So you have to figure out what is the partial pressure of water in there, and you need to get rid of it to have the pressure of H2. Once you have the pressure of H2, you should be able to get the moles of H2 through the ideal gas law. And honestly, that's all I'm going to tell you. Does that make sense?
Yeah, thanks. Okay, thank you. Have a great day.
I have a question on, I have version C
Yeah.
and it's on 11.
And what is number 11?
It's it shows pictures A, B, C, and D.
Right.
And then it's asking which would have a greater melting point and which would have a greater enthalpy of fusion.
Yeah. Okay, so when you look at those pictures, what is your version again?
Version C.
I think I have to get the picture. So hold on a minute.
Okay.
God, why does this look so terrible? Does your exam look bad? There's something.
Not really. Some of the pictures moved around because of the document, but it doesn't really look bad.
My version looks terrible. Jeez. Oh, this is better. I'm really relieved.
Mhm.
Okay. Oh God, it's taking me forever to do this. Okay, here it is. All right, so this is the picture, right?
Yeah.
So which has a high, so what you've got to do here, you've got to think about what type of solids these can be. Okay. And so you have to think about, what do you know about melting points? What about a molecular compound versus, say, an ionic compound, or a covalent network compound? Which of these has like higher melting point? Well, you have to think about what's holding them together, right? In a molecular compound, you've got individual molecules, right?
Mm-hmm.
And they're held together by intermolecular forces.
Mm-hmm.
In an ionic compound, I don't know, I'm just gonna, I can't draw a fancy one. But you basically, what are these things here? These are charges, plus, minus. So these are what kind of bonds? What's it called? It's called an ionic bond, right?
Yeah.
So, and in a covalent network compound, I don't know, I'm just gonna covalent, these are all covalent bonds.
Mhm.
So when you melt a molecular compound, you're breaking intermolecular forces. When you melt an ionic compound, you're breaking ionic bonds. When you melt covalent network, you're breaking ionic bonds, okay? So this is
Okay.
much harder to do because of the
Mhm.
strength of bonds.
Mhm.
Also, the delta H of fusion is going to be different because which is going to require more energy to melt, a molecular compound or an ionic or covalent network compound.
Ionic or covalent ones.
So now what you have to do is you have to look at these pictures. And you're asked to compare. This is D here. It's kind of rubbed out, but of course it's D. You need to figure out, are any of these molecular, or, you know, the ones that you're referring to, is, you know, are they different from you? Are they both molecular, molecular ionic? You know, what?
It's asking, it's A or C.
Okay.
For
And
the-
which has a greater melting point, A or C?
Mhm.
Okay. So if you can figure out which of those is molecular, then I think you will know the answer to that question.
Okay, yeah. Yep.
Yeah, and then molecular would have which, a greater or a smaller melting point?
A smaller.
Yeah, that's kind of where we are with this.
Okay. Thank you so much.
You're welcome. Bye.
Have a good day. Bye.
Bye-bye.